And I would like to thank the organizers for allowing me to speak here. So my talk today, these slides are actually available on my homepage. So just in case you find it like I'm going too fast, you are welcome to download and open it on your phone or laptop. Yeah, so much of what I'm going to talk about today is a joint work with Glenn Grady at Wichita State University in Kansas. Plus, there's some additional work in progress that is being written up. Let's see. So without any further ado, let me just state the main theorem for today. It's a classification of extended conformal field series in the sense of Siegel. So these are functors from the two-dimensional fully extended Bordism category, where Bordisms are equipped with a conformal structure. And Bordisms are in dimensions 0, 1, and 2. And these are functors from this Bordism category to some arbitrary symmetric monoidal target category, true category actually. And in this talk, I'm not going to concentrate on any specific target category. So this classification works for any target category, and maybe you can think of it as giving you a starting point in case you're interested in specific targets. You can use it as a starting point to classify even further depending on the properties of the target category you have. So the theorem, roughly speaking, and this is a almost precise statement, but many details have to be omitted, of course, is that the category of all such functors from the Bordism category to the target category is equivalent to certain gadgets. These are representations of a certain infinite dimensional Lie group. These are not quite representations in the usual sense. They are, first of all, homotopy coherent or infinity representations, so morphisms of infinity groups. And there is an additional condition that says certain elements must go to Serre automorphisms of the target. So let me say a few words what the actual group is. So the group that is present here is a semi-direct product of R2, which is basically translations, and a universal covering of the group of germs of homomorphic maps from an open neighborhood of 0 to the complex plane. So such germs can be expanded using Taylor expansion. These are just power series convergent with some positive radius, and the coefficient, the free term is 0, and the coefficient before the first power of z is non-zero, so that you actually have an automorphism, an invertible, a power series that is invertible up to composition. So the group operation is a substitution of power series. Then we take the universal covering of this group, which basically amounts to replacing the coefficient A1. A1 so far takes values in invertible complex numbers, and we take the universal covering of that. This gives you an infinite covering of the punctured plane, and that's a group. The last condition, the Serre-Twisted condition, tells you that if you restrict to the kernel of this universal covering map, which is just integers, these integers, their values are prescribed. They are given by the Serre automorphisms of your target object. So this functor, the functor from the Bordism category, to the target category, it sends the point to an object, and this group acts on this object, and the action of the integers inside this group is given by the Serre automorphisms of this object. So just as a simple example, in case the Serre automorphisms happen to be trivial for your object, then you simply get the more or less representations in the usual sense of the group, which is not where you don't take the universal covering. So just germs of conformal automorphisms of an open neighborhood of zero. Yeah.
If I had a TFT, 2D TFT fully extended, I could view it as a conformal field theory. So does that mean that in that case you sort of think about most of the conf2 acting in a really boring way, or just?
Yeah, I mean, if for the topological case, I mean, you will see basically most of the conf2 disappearing. I mean, R2 will be contractible, and you will basically see an action of a circle that's precisely the O2 action. Well, strictly speaking, the SO2 action, but since we already picked the positive point, the Z mod 2 will act by taking the dual object. So it's precisely the sort of, you can think of it as a geometrically enhanced version of the O2 action on a fully dualizable object in a symmetric monoidal 2 category. Yes. And at this point, probably I should also mention very briefly that there are variants of this theorem. Like there is a variant that classifies twisted or relative functorial field series, where you have a twist, which is itself a field theory of a similar type, and a twisted theory is a natural transformation from this twist to the trivial twist. And this result is powerful enough to basically accommodate such a setup. And maybe another option I should mention is a chiral conformal field theory, where basically in the setup of Siegel means, roughly speaking, that everything becomes holomorphic. And again, the setup is sufficiently powerful to handle holomorphic families and holomorphic dependence of the output data on the input data. And there are many other variants. For instance, something I'm not going to talk about today is an application to 2-1 Euclidean field series defined by Stolz and Teichner, but maybe that's best left for another talk.
Just to make sure where the action is happening, it's acting sort of on the object in your target category, which you assume to be fully self-dual.
Yeah, so it's a fully dualizable object in a symmetric monoidal 2 category, and then the group acts by, you have a homomorphism from this group to the group of automorphisms of this object. And more precisely, these are infinity groups, which you can, depending on your preference, model as simplicial groups or some other model you like. Yeah. All right, so any questions so far about this statement?
In particular, due to the fully dualizability assumption, you have finiteness built in if you were thinking of a traditional target space like vector space.
Yeah, if you really insist on traditional target spaces, yes, but there are also tricks to sort of, if you want, you may ask, like, can I have infinite dimensional Hilbert spaces and bounded maps? And there is a trick to sort of bring them into the setting by, well, I can only give you like a very crude answer. You can take the free construction, free symmetric monoidal category with duals on the symmetric monoidal groupoid, or sorry, on just the ordinary groupoid of, say, Hilbert spaces and invertible or unitary maps. And basically, the cobordism hypothesis with defects in dimension 1 tells you that the free construction is non-trivial and interesting. And it's something you can, in dimension 1, you can describe it very explicitly, for example. So it is non-trivial, and you can have, it is possible to have infinite dimensional Hilbert spaces in this setup. Yeah. All right, let's move on. Yes. Many talks in this conference were about topological field series. So maybe I should say a few words to emphasize some differences between topological and non-topological field series, and also like some features of the setup that we use here. There are some features common with topological field series, for example, locality, which is a required property, which is also what Ben talked about in a previous talk. So all bordisms have corners in all codimensions, starting from dimension 0. Also, for the full classification theorem, we also want to include isocopies. So instead of just taking as true morphisms, diffeomorphism classes of bordisms, we really want to include the whole diffeomorphism, the homotopy type of the diffeomorphism group. And this diffeomorphism group must respect, also the diffeomorphisms must respect the geometric structure that happens to be present on your bordisms. However, if you don't like infinity true categories, it is possible to work with a true truncated target, in which case the bordism category reduces to maybe much more traditional bordism category where you have just diffeomorphism classes as true morphisms. So the traditional setup is also covered by this formalism. And maybe much more sort of interestingly, I want to emphasize that all bordisms are equipped with geometric structures. And geometric structure here is understood in a very general sense. So probably the first examples, or the ones I'm aware of, is Dmitri Pavlov, of course, who introduced conformal structures. And I should also mention the work of Stolz and Kreitner on other types of geometrically structured field series. And as an example, like not only allow conformal structures, but maybe also Riemannian or Lorentzian metrics, principal G bundles with connection or gauge fields, and maybe some higher gauge fields as inspired by constructions coming from physics, like Kalb-Ramon or Ramon-Ramon fields, co-cycles in differential K-series. So these are all allowed by the formalism. And that's maybe what the main difference between this formalism and traditional topological field theory. And smoothness, that was very fortunately also mentioned by Ben. It shows you that if you have a smooth family of bordisms, it maps to a smooth family of values in the target category. And so in the mathematical formalism, this amounts to making everything into a sheaf of infinity D categories. Okay, so and I will not be able to give you like a precise definition of a bordism category in this talk, but these are the main distinguishing features. Okay. So let me say a few words about how the proof works. There are several ingredients in the proof. Maybe the first ingredient is we prove, I mean, of course, from a physics viewpoint, maybe that's something that's completely trivial, but mathematically speaking, it's a difficult result to prove that extended field series are actually local. So locality here is formulated mathematically by saying that the bordism category with a geometric structure S depends homotopy co-continuously on the geometric structure. And this amounts to saying, roughly speaking, if you have a quantum field theory with some target manifold, then you cover this target manifold by an open cover and define a QFT on each element of the open cover, and they happen to be compatible on the intersections, then it is possible to glue them to a QFT defined on the entire manifold. So that's very roughly what it means. And an argument already present in papers from early 90s by these capsing papers by Frege and Lawrence that discuss why sort of being extended implies locality. So we prove a rigorous version of this statement for geometric Bordism category. So that's the first paper. Another ingredient is what is now called by a case starting from Christ-Schumer-Priest, the relative geometric cobordism hypothesis, which tells you how if you have a functorial field theory where in the top dimension you restrict to bordisms that admit a Hengel decomposition with Hengels of index at most k, how to relate such field series to a similar type of field series where bordisms are restricted to have Hengels of index at most k minus 1. And this statement, in mathematically speaking, amounts to proving a certain, establishing a certain push-out square of bordism categories, where these two bordism categories will be present, and the push-out square will sort of add a free adjunction to the source category. So that's what most of the second paper is about. And then there's an argument which in the topological case is due to Jacob Uri from way back from 2009, which explains how sort of in a rather clever way you can combine, you can leverage the relative geometric cobordism hypothesis, which in Jacob's paper is stated as claim 3417, I think. How to use that to prove the full geometric topological, in Jacob's case, cobordism hypothesis, which allows you to compute the entire space of a functorial field series, so functors from the bordism category to some fixed target category V as a space of maps. And in the topological case, these will be maps of spaces or simplicial sets or homotopy types, if you want. In the geometric case, these will be maps of sheaves on the, say, the side of smooth manifolds or holomorphic manifolds or whatever type of geometric family you happen to be working with. And there's also an action of the orthogonal group built in the topological case. This is also present in this setting. Maybe we prefer to express it in a different but equivalent form as a sheaf on the side of d-dimensional manifolds and open embeddings with isocopies, with embeddings and isocopies of embeddings as morphisms. And such a geometric formulation also allows you to maybe explicitly compute and maybe explicitly describe the action of the orthogonal group for some geometric examples. And finally, specifically for the case of conformal field series, there is an additional complication you have to do of the right side here. You can further compute this and actually obtain the statement I mentioned at the very beginning with the infinite dimensional Lie group. I'm not going to do the complication, but just to mention some ingredients. Then going is some homotopy theory like Williams theorem A and Thomason's theorem on homotopy colimits, and some classical results from complex analysis like the Riemann mapping theorem. Okay, so these sort of are the main ingredients, and everything is available on the archive, part 1 and part 2 in these papers. The argument in part 3, the geometric version, is also written up in the second paper. And number 4 is currently being written up. And let me conclude by maybe mentioning some further applications of the geometric cobordism hypothesis. Just to give you a few examples, we have a classification of invertible geometric functorial field series. So these are classified by what we call the geometric Madsen-Tillman spectrum, which is actually not a spectrum, it's a sheaf of spectra on the side of smooth manifolds or whatever side you happen to be working with. And this extends the previous work, of course, by Galasius, Madsen, Tillman, Weiss, and Buckstedt, Madsen, and Chris Schromer-Priest. Another thing that may be worthy of mentioning, especially in relation to the classified spaces of field series that were mentioned in several talks, there is a proof of a conjecture by Stolz and Treichner, which says that concordance classes of fully extended functorial field series have a classified space. So why is this interesting? It's interesting because this allows you to construct spectra out of spaces of functorial field series. So a spectrum is a sequence of spaces, and each of those spaces can be obtained as a classified space in this sense from extended functorial field series, maybe twisted by some twist that depends on the degree of the space in your spectrum. So this construction also enables the construction of classifying spectra of families of twisted functorial field series. I already mentioned maybe there is a version of this result for two one-dimensional Euclidean field series. This relates to the Stolz-Treichner program. And maybe let me also mention the work of my co-author, Gan Grady, on classification of deformation classes of reflection positive invertible geometric functorial field series. So this is stated as a conjecture in a paper by Glenn Fried and Mike Hopkins on reflection positivity. So this proof basically leverages the locality property to prove this conjecture. And I think this is a good time to stop, and thank you for listening.